Hi everyone, today we will discuss topic 4.2 which is apply concept second law. So welcome to the class. This is the lesson for the day. The first one is the property diagram involving isentropic expansion and compression process. So this is the block diagram for power cycle. Power cycle, which is a steam power plant that consists of boiler, turbine, condenser and compressor. So what happened to each process for this? This is the process that happened in power cycle, which are 4 to 1. 4 to 1 is from the compressor or pump to the boiler. This one is in and this one is out for boiler. So 4 to 1, the heat energy is supplied to the boiler, resulting in evaporation of the water. Therefore, the temperature remains constant. Example of device like boiler, nuclear or generator. So at there, it involves of heat Q equal to H1 minus H4. H is enthalpy. So H1 is out, H4 is in. And then for process 1 to 2, in for turbine at 1 and out for turbine at 2. So the process involved is isentropic expansion takes place in the turbine. So the device is turbine. In the turbine, it involves work W, work which is H1 minus H2. And then for process 2 to 3, which is condenser, 2 in for condenser and 3 is out for condenser. So the process is condensation. Therefore, the temperature remains constant. So for the process, it involves heat, which is H2 minus H3. And the last one, process 3 to 4, which is 3 is in for compressor or pump, and the outlet or out is at 4. The difference between compressor and pump, compressor is the device that used to compress or increase the pressure of gas. But for the pump, the function is to increase the pressure of fluid, either water or oil. So for the process 3 to 4, it is a isentropic compression of the wet steam. Then it's returned to initial state. So it involves the process using work, which is work 3 for H4 minus H3. Next is for the power cycle. We have two cycles that we will discuss. The first one is Carnot cycle. So for the heat engine, the most efficient possible is Carnot cycle. Actually, Carnot cycle is an ideal cycle. Okay, the cycle consists of two isothermal process joined by two adiabatic process. So isothermal at the boiler and condenser, and then adiabatic in turbine and pump. Since all the processes are reversible, the adiabatic process in the cycle are also isentropic. Isentropic means the entropy is same at 1 and 2. Means S1 equal to S2, S3 equal to S4. Okay, this is a TS diagram to represent the Carnot cycle. T1 means T at the higher temperature, TH. T2 is TL, lower temperature. So, for the T, you can refer to the steam table to find the saturated temperature. The other one for cycle is Rankine cycle. So Rankine cycle is a practical cycle. It means the cycle is normally used in the real world. But for the Carnot cycle, it is just an ideal cycle, not used in practical. Why need Rankine cycle? It is because it's difficult to stop the condensation at point 3. Means for the Carnot cycle, point 3 is a liquid vapor. So if we use Carnot cycle, state 3 have some difficulties to compress it by using pump. But for the Rankine cycle, point 3 is saturated water like this here. So it is more easier to compress by pump. Okay, other than that, it needs more work, bigger pump to compress a wet steam compared to saturated water. If the state 3 is saturated water, the pump has much smaller dimension, simple and less expensive. So that means for the point 3 at the Rankine cycle, the phase is saturated water. So the pump will compress the saturated water easier compared to the Carnot cycle that the region is liquid vapor or wet steam. Okay, here is the process for the Rankine cycle at 4, 5 and 1. Constant pressure heat addition in a boiler. 1 to 2, adiabatic expansion taking place in the turbine. 2 until 2 to 3, constant pressure heat rejection in the condenser, and 3 to 4 is adiabatic compression of water in the feed pump. Actually, the process in the power cycle in both cycle for Rankine and Carnot is same. For the Rankine, we also have boiler here, turbine, condenser and pump. The difference is the region for state 3. which is for the Carnot cycle, as I mentioned earlier, the region is mixture of liquid vapor. But for the Rankine cycle, the region is saturated water. Okay, next. Here is the formula that you can find on your formula sheet for the chapter 4. So for the power cycle, here are the formula. The first one is efficiency for Rankine. This one is work ratio, RW. This one is SSC. SSC means specific steam consumption. Okay, SSC. So in this chapter, for the Rankine and Carnot, we will calculate or find the value of efficiency, work ratio, and specific steam consumption. For the Carnot, it is the ideal cycle, so it also can use this formula. Because Carnot cycle is heat engine and it is an ideal cycle, so we can use this for Carnot. But for the Rankine, we only can use this formula. In addition, for the Carnot, you can use this formula, heat engine, and also can use this formula for Carnot. Okay, in conclusion, that means this formula can use for Rankine and Carnot, but this formula can only be used for Carnot cycle only. Okay, for using it in Carnot cycle, we need to transform it to the properties of temperature. Means 1 over TL over 1 minus TL over TH for the efficiency for Carnot. It is same as heat engine that I explained before this. Okay, so for the work turbine, work pump, and Q boiler, we can find the properties using this formula. Means this one is WT is turbine work. WP is pump work. Q boiler is Q in, which is Q supply in boiler. So this formula is relates to this formula, means WT, this one is WT, this one is WP. But for the Q boiler, this formula, we can modify it to the H1 minus H3 minus H4 plus H3. So H3 will be eliminated. Then the formula became H1 minus H4. This one is Q boiler, Q in. Okay, so to find the efficiency, work ratio and SSC, you need to find all the enthalpy, means H1, H2, H3 and H4. Then substitute the value into this formula. So let's go to the discussion. Discussion for tutorial for 2. Okay, the first one. For the Carnot cycle, a steam power plant uses the Carnot cycle. Okay, so we can draw the TS diagram for Carnot cycle. So here the T, S, P1, P2, one, 2, 3 and 4. So here S1 equal to S2, S3 equal to S4. So from the question, we know that the cycle have 2 temperature. So that means the larger one is TH and the lower one is TL. So we can put it here, TH 500 and then TL 50 Celsius. Don't forget to convert temperature into Kelvin. Okay, the first question. The efficiency of the plant. As I mentioned earlier, for the efficiency, we can use the heat engine efficiency, the formula for heat engine efficiency, which is 1 minus TL over TH. So, Carnot efficiency equal to 1 minus TL over TH in Kelvin. So, for the TL, so 50 plus 273, we will get 323 divided by TH, 500 plus 273, that's it's 773. So you need to solve the value in the bracket first. So 1 minus 323 divided by 773, the answer is 0.58. Then the final answer, don't forget to times with 100% because the question asks about the efficiency. Usually for the efficiency, the value, we convert it to the percentage. So the answer is 58%. So the value is 58%. And then question number 2. The net power output. Net power is work. So work in kilowatt. How to solve this? So in this question, also given the value of heat at boiler. Means this one is Q in. Or in other words, it is QH. So we know for the heat engine, we also can use N Carnot equal to W divided by QH. So we already get the efficiency 58 divided by 100 equal to W, then the QH is 25. So we will get the answer 14.5 kilowatt. And then the third one, the heat removed by the condenser. Heat supply to the boiler is QH or Q in. So for the condenser, it is Q out or QL. Means the lower heat compared to the boiler or supply heat. Supply heat must be always larger than heat rejected or heat removed. So we can use the second law formula, which is W equal to QH minus QL. So W 14.5, QH is 25. Then you can find the value of QL, 25 minus 14.5. So QL equal to 10.5 kilowatt. Okay, that's all for the question number 1. And then we go for the question number 2. For the Carnot cycle, a steam power plant is based on the Carnot cycle. So it is confirmed the cycle is Carnot cycle. The boiler is supplied with saturated water at 20 bar and produce dry saturated steam at 20 bar, and then the condenser operate at 0.1 bar. The mass flow rate means m dot. Calculate the following: the thermal efficiency. The different question 1 and question 2. Question 1, it's given the value of temperature. But for the question 2, it does not give the value of temperature, but the question give the value of pressure. This one is, the higher one is pH, P high. This one is P low, P at low temperature. So first, we need to draw the TS diagram for this question. TS, and then the curve. So this one is P1, which is 20 bar, and then P low or PL 0.1 bar, 0.1, 0.2, 0.3 and 0.4. So here S1 equal to S2, and this one S3 equal to S4, which means isentropic process. So to solve this question, we need to find the TH and TL. So how to find the TH and TL? Refer to TS at pressure given. It means refer to steam table, find TH at high pressure. High pressure is 20 bar. So the TS is 212.4. Means TH okay, TH equal to TS at P high. PH, P equal to 22 bar, which is this one, 212.4. Don't forget to convert into Kelvin, which is plus 273. So for the TS, not TS, TL equal to TS at P equal to 0.1 bar, which is okay, here is P 0.1 bar in your steam table. Then the value of TS is 45.8. So the value is 45.8 plus 273. So here you will get the answer 405.4. Then for this one, 45.8 plus 273, you will get 318.8 Kelvin. Then the first question, the thermal efficiency. So thermal efficiency for heat engine or Carnot is 1 minus TL over TH. Means 1 minus TL is 318.8 divided by 485.4. So the answer is 0.34, then times with 100%. So the final answer is 34% for question number 1. Then for the question number 2, ask about power output of the turbine. Power is work. So this question means WT. If you forget the formula, you can refer to the formula sheet here. So from this formula sheet, WT or turbine work is H1 minus H2. This one. So what we need to do is we need to find H1, H and H2. Okay. So the first step for question 2, work turbine, find H1 and H2 because the formula is H1 minus H2. So how to find H1? Step 1, H1. Refer to the TS diagram. H1 is at saturated vapor line. Here, this one, Point number 1 is saturated vapor. But for the number 2 here, the point is liquid vapor. So saturated vapor means we need to read at steam table at G, vapor or gas or steam. So we find the H at G. Means for the H1 equal to Hg at P. Point 1 is at 20 bar. So H1 equal to Hg at 20 bar. So refer to the steam table. Then you will find the value of Hg at 20 bar is 2,799. So that is the answer for the Hg. 2,799. And then step 2, how to find the H2. So before this, in chapter 2, we already learned about the liquid vapor that use the special or the mixture liquid vapor formula to find the properties. So for the H2, actually the formula is H2 equal to HF plus HFG. So we need to find the dryness fraction because the phase is a mixture of liquid vapor. So we need to know what is the proportion for the HF and HFG, or the proportion for liquid and vapor in this formula. So the problem is we don't know the X value. So how to solve it? We can use the isentropic process, because at this point the value of S1 is equal to S2. For the S2, we don't know because S2 is SF plus SFG. But for the S1, we can read at the steam table same like H1 because it is the same point, which is at saturated vapor. So the step 2, S1 equal to S2 equal to Sg at 20 bar. Okay, the value is Sg is 6.34. So 6.34 for the Sg. Then we write down the formula for the S. S2 equal to SF plus SFG at, for the point 2, here the pressure is 0.1 bar. So at 0.1 bar. Why we need to use this formula? Because we want to find the X value. So S2 we already know, S2 equal to S1. So the value is 6.34. And then for the SF and SFG, we can refer to the 0.1 bar. So 0.1 bar the value for SF here, and then the value of SFG is here. So SF 0.649, 0.649 plus X, then the SFG is 7.5. So from here, you can find the value of X, which is X equal to 6.34 minus 0.649 divided by 7.5. So we will get for the answer 0.758. So I round up to 2 decimal places, so it will become 0.76. After we find the X, so we can calculate for the H2. So H2 equal to HF plus X HFG at 0.1 bar. So HF at 0.1 bar is 192. So 192. The X value is 0.76, and then for the HFG, the value is 2392. So we can calculate the value of H2. The answer is 2009.92. So after we find the value of H1 and H2, substitute the value into work turbine. So work turbine equal to H1 2009.92 minus H1 is 2007. Okay, make sure you substitute the right value. 2799 minus 2009.92. So the answer for turbine work is 2009 minus 2009.92. WT is 789.08 kilojoule over kg. Why kilojoule over kg? Because H here, the unit for enthalpy is kilojoule kg. How about the question number 3? Heat transfer into boiler. So for the boiler, heat for the boiler is a Q boiler. So refer to the formula for the Q boiler. So Q boiler is H1 minus H4. So we already have H1 for question number 3. We already have H1, but we doesn't have H4. So how to find H4? Because Q boiler equal to H1 minus H4. So refer to the TS diagram. Point 4 is at saturated water. This one is line for saturated water or saturated liquid or fluid. Means if we want to find the enthalpy here, we need to read at F, mean HF. This one, saturated vapor, HG. So, to find H4, it is the step number 3. H4 equal to HF at, okay, number 4, the pressure is at high pressure at 20 bar. So, refer to 20 bar, the HF is 909. So, here the answer is 909. So, we can substitute the value for the Q boiler, which is Q boiler equal to H1 2799 minus 909. So, you will get the answer 1890 kilojoule over kg for the Q boiler. So, we already finished. Find the answer for the question 2, but I need to add about the calculation if the question asks to find the work ratio and SSC, specific steam consumption, for the Carnot. So, if question asks the work ratio or Carnot, okay, you can add this solution. You can use this solution, which is in the work ratio formula here. This one. So for the work ratio formula, we have WT minus WP. This one. Okay, this one is W net. W net is network is WT minus WP. Same goes for SSC. We also have W net. So, to solve the question about the work ratio and SSC for Carnot, we need to find the W net first. So, how to find the W net? We can use the efficiency formula. Okay, as we know, efficiency formula is here, either the TL or the another one is, okay, let me show you this one. Okay, W net divided by QH. So we know that efficiency of Carnot equal to W net divided by Q boiler. And we also have the value of Q boiler. So the efficiency is 34%. 34%. We need to find the W net, and then the QB is here, 1890. So we will get the W net value is 34 divided by 100 times with 1890. So the answer is 642.6. So after you get the W net, you can calculate the value for the work ratio. Okay, so formula for work ratio, the symbol is RW. Okay, work ratio equal to, you can refer to your formula, W net divided by WT. So, W net divided by WT, which is W net is 642.6, and then WT, we already get this for WT, 789.08. So for the word ratio, you will get divide by, okay, so you will get 0.8144. Word ratio, it doesn't have the unit because it is a ratio of W net divided by WT. How about SSC? So, you can refer to the formula for the SSC, which is 3600 divided by W net. Okay, so SSC equal to 3600 divided by W net. So, W net is 600. Okay, here, W net 642.6. So, the answer is 3600 divided by 7 and 6. 642.6 is 5.6. The unit is kilogram over kilowatt hour. Okay, that's all the solution or the way to find the properties for the Carnot cycle, which is efficiency. Okay, and then word turbine, Q boiler, word ratio, and also SSC, specific steam consumption. Okay, so for the question number 3, you can try on your own because the question is have same solution as question 2. But the pressure is different, which is 50 bar and 0.05. So question number 3 asks about the TS diagram. Sketch the TS diagram. So you can sketch like I showed it to you before, this one. And then efficiency, we already discussed it here. And then also for the heat supply to the boiler means Q boiler. So you can try it later. Okay, next is a Rankine cycle. How to solve the problem for the Rankine cycle. So the question is like this. A steam power plant operates between a boiler. So the question will given two pressure, the higher one and the lower one. So same as a Carnot cycle, first we need to draw the diagram. So for the Rankine cycle, we make the curve and then the, okay, so for the Rankine, okay, it is like this. So P height 40 bar, the higher one is here 40 bar, and then here is 0.0 0.065 bar. So for the Rankine, 0.1, 0.2, it also has isentropic process, which S1 equal to S2. And then we have point number 4, point number 3, not 4. Point number 3, number 4, and number 5 here. So this is a TS diagram. So the question asks about determine this limit. For this limit, the cycle efficiency. So cycle efficiency with dry saturated steam. Dry saturated means at point 1, after the steam exit the boiler, it in saturated steam. So for the cycle efficiency for Rankine, if you refer to this formula, H1 minus H2 minus H4 minus H3 and H1 minus H3 minus H4 minus H3. So that means we need to find H1 until H4. Then substitute the value into this formula. Don't forget, for the Rankine, we cannot use this formula. This formula is for Carnot only. So, the first step and second step to find H1, H2 is same like Carnot cycle. Okay, this one. Step 1 and step 2 for Carnot, and Rankine, it is the same solution. Or it is the same step. Okay, so how to solve it? First, we need to find the H1. So H1, same as Carnot, equal to Hg at 40 bar. Okay, Hg here. So 2801. Then step 2, we use S1 equal to S2 to find the X, then use X to find the H2. So S1 equal to S2 equal to Sg at 40 bar. So the value is here 6.070. And then S2 equal to Sf plus X. Sfg at the low pressure 0.065 bar. So S2 we already know 6.070. Sf and Sfg rate at 0.065 because point 2 is here at low pressure. So Sf, we put Sf, and then X. Sfg is here, 3.273. So you will get the X value 6.070 minus 2.797 divided by 3.273. Sorry, I read at the wrong value, at the wrong pressure. So for the Sf and Sfg, we read it at the P low, 0.065. So the value, it is not this one, but this. Okay, so Sf and Sfg. So Sf 0.541 for Sfg 7.760. So for the X, you will get 0.71. Then we use the X to find the H2. HF plus X HFG at 0.065 bar. So HF is here. HFG is, this is HFG. So HF 158 X 0.71, HFG 2402. So the answer for H2 is 1870.52. Okay, how about the step to find the H3 and H4? So for the Rankine cycle, H3 is also at saturated water like Carnot. Okay, you can see here. But for the Carnot, the point is 0.4 saturated water. But for the Rankine, 0.3 is at saturated water. 0.3 here is saturated water. So, to find the H3 equal to HF. Okay, then we go to the step 3. H3 equal to HF, but the pressure is at low pressure, 0.065. Okay, you don't need to find or to read again the steam table for HF because you already have the value of HF here. Okay, HF for 0.065 bar is 158. Same here. Okay, then we just write down the value. Okay, so the value is 158. Then the last step, we need to find H4. So how to find H4? Actually, H4 is compressed liquid. This one is compressed liquid. So for the compressed liquid, we use the formula that is modified from H equal to U plus PV. U is small, then we can neglect the U. So H equal to PV. Then from that, we modify the formula. It will become, which is H4 minus H3 is work pump equal to H4 minus H3 equal to VF P high minus PL low. So this P must be in unit kilopascal or kilonewton over meter square. Okay. So VF, actually VF, the value is different for the difference of pressure, but the value of VF is small, that is 0.001. So we just assume the VF equal to 0.001 meter cube over kg. So to find the work pump, H4 minus H3, it means 0.001. Then P high is 40 times 10 power of 2. To convert it to kilopascal, and then minus 0.065 times with 10 power of 2. So you will get the answer 0.001, 40 exponent 2 minus 0.065 exponent 2. So you will get the answer 3.9935. Usually the value for work pump is a small value because work pump is work used in the system, so it is small than the work supply or work out, W turbine. So here we already have H1, H2, H3 and also H4 minus H3. Then you can use the formula for the Rankine cycle here. This formula. Okay, Rankine cycle. So Rankine cycle equal to H1. Just copy it from your formula, H1 minus H2 minus H4 minus H3. Then H1 minus H3 minus H4 minus with the H3. So H1, substitute the value, H1 minus H2 here, H2 and then for the H4 minus H3, because we have H3 and then we also have H4 minus H3. So just put the value H4 minus H3. So here is 3.9935 divided by H1. Okay, and then H3. H3 is here 105.8, and then this one is H4 minus H3. Okay, so you will get the final answer. Calculate the value. So you will get 0.35. Then don't forget to times with 100. So the answer is 35%. Okay, how about if question asks the work ratio and SC for the Rankine cycle? Okay, to help you calculate it easier, you can add the value for this, because for the work ratio we use W net. So W net is WT minus WP, which is this one. Okay, this one is WT, this one is WP. So just calculate WT minus WP. Okay, so if the question asks about work ratio and specific steam consumption, so work ratio. Okay, so first we calculate the W net, which is WT minus WP. So the answer is 2000 801, then you will minus with 1870.52, then minus with 3.9935. So you will get 928.46 for W net. So for the word ratio, just substitute the W net into the formula. So RW equal to, okay, like we discussed earlier, this one, word ratio is W net divided by WT. So W net divided by WT, so W net is, okay, divided by WT, so W net 926.49. So for the WT, you can get from here, this one, WT. So 2,801 minus 1,870.52. So 930.48. So the answer is divide by 930.48. It is 0.9957. Usually for the word ratio, we use 4 decimal places. Okay, so it's same for the specific steam consumption. Just use same formula, 3,600 divided by W net. Okay, so for the SSC, just use 3,600 divided by W net. So W net here 926.49. So the answer 3,600 divided by 926.49 is 3.88 kilogram over kilowatt hour. So that is the answer for word ratio and SSC, specific steam consumption. Okay, this one, word ratio and specific steam consumption, it doesn't have in this question, but I add on this for you to understand the solution. So after this, you can try the solution, or you can try to solve the problem for question number 1. We already discussed. So you can continue for question number 2, number 3, and number 4. But it has a different for the question number 2 and number 3 because the question give the temperature for number 2 and number 3. So what happen if the question give the temperature? It means, okay, the question is same because it give the two value. This one is P high, the higher one. This one is the lower one. But in addition, have the temperature. So how to solve this? Let me show you. First, you can draw the diagram. Okay, so for the 100 bar, you can refer to the steam table, the TS value. So TS value for 100 bar is 311 Celsius. But the question given, temperature of steam leaving the boiler is 400 Celsius. So we draw the TS diagram first here. So it said that this one is boiler here. Okay, the steam leaving the boiler at 400 Celsius. But the TS is 311. So 311 is at here. 400 is above from the 311. Means the phase for 0.1 not saturated vapor but superheated. Why superheated? Because the T is larger than TS. T is 400 Celsius. TS is 311. So let's say the temperature 400 is, okay, like here, 400 Celsius. Okay, just sketch it. So means the H1 is at there. Okay, so from this, same as before. Okay, 0.3 at here. And then 90 degree. Then here. So means for the 0.1, it is different because before this, 0.1 is saturated vapor here. But because of question, give the value of T is higher than TS, means the phase is superheated here. So this is 0.1, 0.2, 0.3 and 4, also 5. So same as before, S1 equal to S2. So to solve this question, it is same like the question number 1, but the difference is at 0.1, which is to find the H1. Why we need to find the H1? Because the question is asked about the cycle efficiency. So for the Rankine cycle, for the cycle efficiency, we need to find all the enthalpy value, H1, H2, H3 and H4. So for the step 1, okay, H1 equal to H at 100 bar, 400 Celsius, superheated. So you can refer to the superheated phase at steam table and find 100 bar, 400 Celsius and read the H value. Same goes for the step number 2, which is S1 equal to S2 equal to S at 100 bar, 400 Celsius, superheated. So read the S and H at the same pressure and temperature at superheated. Other than that, all the step is same as question number 1. So means H1 and S1 only is different, but the rest is same. Okay. So for the question 3, also same, because the question 3 is give temperature. If the question does not give the temperature, so it will become like this. But for the question that give the temperature and then the temperature is higher than Ts at the high pressure, so step 1 and step 2 you can do like this. So you can try for the question number 2, number 3 and number 4. Then I think that's all for this class. Any question you can DM me. So that's all. Thank you.